Good afternoon, everyone. Today, we are going to be learning about decorators, specifically that at syntax that you sometimes see in your Python code. Looking something like at func, and then define f on x, and then do whatever you want. What is this at func business? This is called a decorator, and the goal of today is to be learning what this is and how it works and what goes on behind the hoods when you do something like at func. Okay, now a brief overview of what we're going to be covering today is to understand decorators, we're just going to review the basics of what a function is. In the end of the day, decorators are really just functions being put to very, very good use in Pythonic ways. And so we're going to have a refresher on what functions are, their properties. Following that, Python has a very unique property associated with functions attributed to the notion of first-class functions. And we're going to learn what that is after understanding the basics of function terminology. Secondly, we're going to learn after first-class functions, what we call FCFs. We're going to learn argument packing. Once again, another Pythonic notion related to functions that allows you to pack and unpack variables within a function of arbitrary length. We'll look into what that means. And finally, we'll put all this together to actually understand what a decorator is, how it works, and what goes on behind the scenes. Okay, so to begin, let's just recap what a basic function is and understand some formal definitions associated to functions. Here's a function that basically takes in a list of numbers, specifically the numbers from the range 1 to 5, or sorry, 0 to 4. So you have this list as x, and then we pass it in to square list function, which all it does is it creates a new list, and for every element within this original list, it iterates over each of these elements and squares each of them. And in this case, you can just assume square is a built-in function, or square is a function that just takes in a number and returns the square of that number. When you do such a algorithm, what you get is a list afterwards that squares every number. Once again, I'm not really going to go over what goes on in terms of the code here. It's kind of an expectation that you really understand how that all works. Okay, now after that, what we can do is we can just formalize some of these notions. And to formalize them, the name of what we say, the name of the function is what's put right after the def. It's called f in this case. We have function parameters, which is what the function consumes. And I want to differentiate parameters with arguments because arguments are what you pass into the function. Arguments can be different upon function call. However, the parameters are fixed as they get defined when you create the function, when you define the function. And lastly, there's the body of the function, which just tells you what the function is doing at the indent after the def statement. Okay, once again, just largely just a refresher in regards to what a function is. All right. Well, following this, we have the notion of first-class functions. This is probably the first. If you don't know this already, this is something that's somewhat specific to Python and languages like JavaScript and very high-level languages. More lower-level languages like C and C++ typically don't implement first-class functions. And what is a first-class function? Well, we'll get into that in a second. But the properties of first-class functions are it allows you to nest functions within other functions. You can return functions, and lastly, you can assign functions to variables. And what you can do is take the notions of nesting, returning, and assigning, combine them all together, and that gives you some really, really cool properties that you can leverage with functions, and we typically denote those as the properties of first-class functions. Okay, so what is a first-class function? Well, a first-class function really just means that a function is treated no differently than an integer or a string or any other type in Python. And this should be evident because the whole notion of first-class functions is we want to nest functions within functions, return them, and assign them to different variables. Therefore, that's why they are kind of the same as integers and strings. We can do all those things with integers and strings and function. And these are really first-class variables or first-class citizens within the Python language and as are functions. Okay, and so the first aspect is you can nest functions within functions. And this is shown here through a nice example where all we're doing here is adding two numbers, but you're doing them by simply calling f. You're calling f with one variable, and within f, you're not just doing basic arithmetic, but you're defining another function called g, and g now takes the return value of g is now the sum of x and y. Okay, so just another fancy way of doing addition. It does work functionally a little different than if you had one function taking in two variables. And let's just see in code exactly what this does. So what I like to do is I like to flip over into two environments. One is this slide deck, and the other environment is a terminal where I can do a lot of coding and show you guys live examples. And so let's actually just see this notion of nesting, and I'm going to define it or show you it, demonstrate it through a file called nesting.py. And then here what I'll do is I'll have some global variable x equals 10, and then I'll define a function x. Again, this code is all the same code you have available on the slides if you want to follow along. And then within this function, what we do is we define another function, g of y, and here we just simply return x plus y. And now going back to what f does, this is where indents in Python come in handy, because the indent is over here, where we're really in the body of f at this point, as opposed to body of g, which was line 5. And within the body of f, let's just return g of x. Okay, so now if I called f on x over here, what would this do? Well, x over here would be this global variable, so we would pass in 10 over here. And what f would do is it would define another function g, which would take in some variable y, and return x, which is defined up here. This is called a closure, by the way. This is defined up here with outside the function g. That is the notion of a closure, some variable that's defined outside the actual function it's used in. What we're doing here is we're passing in x as y, and then we're simply adding these numbers. And then because f returns g of x, what we really will get here is 10 plus 10. Okay, and so rather than just doing f, let's actually just print f of x. Okay, I'm going to save this file, and then we'll run nesting.py, and we indeed do get 20. Okay, so that's the notion of nesting functions within functions. The next thing we can do with first-class functions is return functions. And this, like I said, is very similar to the previous one, but now rather than returning g of y, which is what we did in the previous example, as you recall, what we're going to do is we're going to return just the function g. Okay, so once again, let's just flip back to our code and see exactly what's going on when we do some code when we do something like this. So this is actually the notion of returning. So I'm actually just going to open up the same file, nesting.py, and it's very similar, but all we're doing now is we're returning g here. Okay, and what would happen if we called print f of x? Well, printing f of x, interestingly enough, will return a function, which kind of does make sense, right? Because f of x returns g, and g is just a function. Okay, so if we just run this without passing in anything else, what we get is a function. It says it returned a function, some fancy local.g stuff. Don't worry about what that is, but overall it returned a function. All right. Well, because we returned a function over here, and for now, let's just go to this print business. It returned a function, and therefore what we can do is we can call this function now. We can say, we can pass in some other number here. Okay, and now, because f of x returned a function, and what we're doing is we're calling that function with the, in this case, number 20, where we're going to return the overall value of 30, because g now returns x plus y. Okay, so printing this, we should, and we do indeed get, oops, Python 3, we do indeed get 30, as we expect. Okay, just clearing up that window so you guys can see once again, we get 30. Okay, so that's the notion of returning functions. And lastly, what we can do is we can assign functions to variables. Okay, and this gets really interesting because now, again, looking at that same example, let's, rather than just calling f on some variable, let's actually assign it to a variable. Okay? And so this is, as you can see, starting to get a little bit powerful. And I will demonstrate that through this example. So what we do is, with this exact same code, we're going to say add 10 is just going to be a variable, kind of like how we defined x up there on line 2. We're going to say add 10 equals f on x. We'll just be put in 10 here. It's the same thing. I just want to be very explicit. And what do we do here? Add 10 is now a function that effectively adds 10 to whatever you pass into it. Okay, so add 10, let me restate that. Add 10 is a function. It's a function, right? Because f just returns g. It's a function that adds 10 to whatever you pass into g. Okay, so now what we can do is really cool stuff. We can do like print add 10 on 20. We can print add 10 on 50. And what we've done is we've really just defined our own function that lets us add 10 to some arbitrary variable. In this case, an arbitrary number, integer. Okay, and if we run this, we should indeed get 30 and 60. We do. Okay, so that's very, very powerful and hopefully pretty cool. Okay, so now that we have this notion of assigning functions to variables, returning functions, and nesting functions within functions, we can combine all these and get a very, very powerful generic function out. And let's walk through this. What does this do? We're going to define a function called adder. And what this is going to do is it's going to take in some number n, and it's going to allow us to define various adder functions of different increments. So for example, we can call adder on 7, and that'll let us define an add 7 function. We can call adder on 20, and that'll let us define an add 20 function. All right, and the code is actually very similar. I'm just changing up some of the variable names to make this more obvious. We have a function, we define another function that simply adds the numbers, and in this case, we return the inner function. And the code's not much different. I'm just putting a lot of the previous concepts together and changing up the variable names, so you can see that this now produces some very powerful notions by letting us define our own arbitrary add increments. Okay, so once again, just looking at this in code, what we can do is taking that same nesting.py example, we'll change up these variable names, be adder on n, and this will be add n on x, and it'll do n plus x, and here we'll return add n. And we don't need this x up here anymore. Okay, and now this is really powerful because now we can do something like add 5 equals adder on 5. Add 10 equals adder on 10. And just to really kill this, highlight this point home and kill it, we can do adder on 20 equals add 20 equals adder on 20. And what have we done between line 7 and 9 is we've defined 3 functions that let us add, in this case, 5, 10, and 20 to various numbers. And so we can demonstrate this by printing add 5 on, let's just say 10. Now let's just make all these give us the same result, actually. So let's just do add 5 on 20. That won't work. Add 5 on 25. Print add 10 on 20. And print add 10, add 20 on 10. Okay, so what we're doing here is we're adding 5 to 25 gives us 30. Adding 10 to 20 gives us 30, and then adding, in this case, 20 to 10, it gives us 30. All 3 of these should give us 30. But with different arithmetic and different functions, as you can see. Okay, so running this code, we do get 30 in all 3 calls. Okay. Awesome. So that's first-class functions for you. Hopefully, something very, very cool, powerful, and something you can leverage within your code later. Now, what we need to do is we need to combine the notion of first-class functions with something called argument packing. And in doing so, we will have the capacity to create decorators. So what is argument packing? Well, argument packing can really be broken into sequential argument packing and pairwise argument packing. And this is done through the notion of args and quarks. Okay, so let's first look at args and how you would pack a sequence of arguments into one variable. So once again, if we wanted to pass an arbitrary amount of arguments into some function, what we could do is use this star args keyword. Oh, sorry, the args is not actually a keyword. It's really the star operator that allows us to do this. And a star will allow us to pack a sequence of arguments together, and quargs, or sorry, the star operator, typically denoted with star quargs, will allow us to pack keyword arguments, pairwise arguments together in the form of a dictionary. Okay, so to pass an arbitrary amount of elements, use args. And what I mean by this is if you just define a function that takes in star args, and again, I want to highlight that this args is not necessarily needing to be called args. You can call this whatever. It's just a typical convention as we call it args. Okay, and then what I'm going to do here is I'm just going to simply print everything I pass in. And as you can see, if I pass in this case, 4 separate arguments into args, we do indeed just simply print out a tuple that contains these 4 elements. Okay, so let's just take a look and demonstrate this with our example. If we, in this case, do args.py, I'm going to show you define f on star args and print args. And then if we call f on 1, 2, hello, the list 1, 2, what we get here is a tuple that contains all the things we passed into the function. Okay, pretty straightforward. And again, I just want to highlight that this doesn't need to be called args. It can be called whatever. And as long as you print whatever, it will do the same business. Okay, so pretty interesting so far. Now, very related to this, we can also pack pairwise arguments in the form of key value pairs using star quarks. And I'm not going to demonstrate this through the terminal, but as you can see, if you just pass in a dictionary to your function, and your function is denoted with star some variable, it will print out, well, quarks in this case will be a dictionary that contains these pairwise relationships. Okay, awesome. Now we can take the notion of quarks, argument packing, as well as the notion of first-class functions, and combine them together to get the notion of decorators. And with decorators, what I want to do is I want to first motivate them through an example that will show you why we use them typically. And then we're going to see some real-time benefits of how you consolidate code with them. We're going to look at the @ syntax that is probably in a lot of libraries you've encountered already. And then we're going to have our complete look at a complete example that really brings the whole lecture together. Okay, so the motivation for decorators can really be done through seeing the arithmetic example we've been working through. What we've seen is an example that allows us to add 2 numbers together. But say, for example, we just wanted to do generic arithmetic operations, add, subtract, multiply, divide, so on and so forth. Well, what we can do is we can combine the notion of first-class functions and args quarks to allow us to write a lot of short generic code to do arithmetic for various operations. Okay, and let's see this through an example. Say we wanted to ensure that only integers are passed into this function. We wanted some error checking to make sure that all this arithmetic that's going on, if someone passes in a string or a list or some other variable, we don't want Python to crash. We want to print a nice error message to the user saying, hey, you should probably just pass in integers given you're doing arithmetic. Okay, so how would code like this look like? Well, you would have a function saying define add on x and y. If the type of x is not an integer, print a message saying x needs to be an integer. Similarly, if y is not an integer, print y needs to be an integer. And finally, if they actually both are integers, return x plus y. Okay, and you would have to do that for the add function, and then as you wrote your subfunction, you would have to do the same thing. And then, as you can imagine, with multiply, divide, modular arithmetic, with all the functions that you do arithmetic operations, you would have to really just duplicate a bunch of code in the form of these if and elif conditions. And as programmers, we know that writing duplicate code is just never really a good idea. Anytime you're in a situation you're doing that, you can typically, well, consolidate code. And that really is where the power of decorators come in. It allows us to generalize all this error checking into some independent function and have our arithmetic happen independently. All right, so how would that happen? Well, again, a lot of duplicate code. We don't want to do this, so decorators will consolidate this code. And the way we can start off consolidating is let's just actually define a function, again, independent of all the arithmetic, that really just takes in two arguments, x and y, and it just simply checks. If x is not an integer and if y is not an integer, just print these error messages. Okay, so nothing too fancy going on here. It's just a function that takes this error checking and isolates it from the arithmetic. Okay. Well, what we can do now is we can take this function, this isolated error checking function, and nest it within a generic arithmetic function. Okay? And what this arithmetic function is going to do is it's going to take in some arithmetic operator, whether it's add, subtract, multiply, divide, whatever you want to do. Okay? And then what we're going to do is we're going to, with arithmetic, all we're going to do is we're going to return validate arguments. That's really the only thing that goes on within this arithmetic function. It defines some function and then it returns something. Okay, and then what's interesting is validate arguments is the function that actually takes in these operations, or sorry, these integers, and calls whatever operation you want on them. But prior to calling this, it actually just makes sure they're both integers. Okay, so this is hopefully very, very powerful and very, very interesting and cool if you've never seen it before. And now we can see this through an example by just having a function called add that takes an x and y, returns x and y. And now this is really the highlight of the lecture right here. What we're going to do is we're going to take our add function and we're going to make it equal to arithmetic on add. Let's just be very clear here. What are we doing? We're making add, which is really a function, and in many cases just a variable, and we're redefining this variable to be the return value of whatever this arithmetic function does. Okay, but let's just be clear. What is this arithmetic function doing? You're like, whoa, whoa, whoa. Am I not changing the behavior of my add function by reassigning it? And what's interesting is you're not. And the reason the add function, the behavior of the add function does not change is because even though you reassign it to arithmetic on add, what's interesting is all arithmetic is doing is returning validate arguments, and validate arguments is actually calling your function. It's actually calling this add function. It's being passed in right here, and then all validate arguments is doing is it's actually calling your function. And then what's really, really interesting is it's just doing this error checking prior to calling your function. Okay, and now what we can do is add, well, it's going to be working with integers, but now if we try to call add with a string, well, this original add function would actually just error out because Python would crash. But now add on high will actually work. Okay. Let's take a look at this. So I'm going to define arithmetic that consumes some function. And then within this function, I'm going to define another function called validate arguments that consumes x and y. And then over here, we're going to say if type on x is not int, print need x to be an integer, elif type of y is not int, print need y to be an integer. I apologize if you guys can hear my keyboard, by the way. Else, return operator on x and y. Okay, and this is the important part. This is, say, for example, the add function gets passed in here. Well, we're still calling the add function. We're still calling it. Okay? And then finally, what we do is within the arithmetic function, we return validate arguments. Okay, and then to demonstrate this through an example, we define add on x and y, and this simply returns x plus y. And obviously, let's just try to do this very slowly. If we print add on 1 and 2, this will do exactly what we expect. The file I called this file decorators.py, by the way. Decorators.py, and we get 3. Okay, but if we try to call add on high and 2, we're going to get an error. Can only concatenate strings, not integers. That makes sense. You can't add high and 2. But watch, if all I do before this line is I say add equals arithmetic on add, well, now the functionality of add has changed to be whatever arithmetic does, which interestingly enough does actually do add. It actually still does add, but it does some error checking prior to doing that. Okay, so now we'll not error out, but it'll give us need x to be an integer. This none is being printed here. I can this is a function of just the print value. I probably shouldn't do a print here afterwards. I should probably just call add here, and now it will do exactly as the slide state. Okay, let's take a look at this code again. I think this is like I said, this is really bringing home everything we've learned into one complex example, and I want you guys to take a moment to just understand this. And this is really, line 15 is really where the difficulty comes in. I highly recommend spending 10 minutes on your own time, pause this video if you need to, spend some time and really just understand exactly what line 15 is doing. Okay, and you can understand this by just walking through exactly what's going on as these variables get passed. Okay, so that's decorators for you. Now, how is this going to be related to that at syntax we've seen earlier? Well, what's interesting is this at syntax is actually just a short form for something we've already seen. What we can do is, if you do something like at arithmetic, and again, let's just recall what arithmetic is. Arithmetic is just this function. If you do at arithmetic, this is actually equivalent to doing add equals arithmetic on add. Those lines are indeed equivalent. Okay, and so Python, the add syntax, believe it or not, it's just a short form for line, for this line right here. Okay, so as long as you understand what this line is doing, that add syntax is nothing more than syntactic sugar. Okay, and so therefore, you can just think of this really being replaced with, and again, you kind of have to do it afterwards, not necessarily before. It would be add equals arithmetic on add. Okay, this is equivalent to at arithmetic. The only difference is this is, of course, going on top of the function, while this would have to go below the function based on how Python reads code from top down. Okay, cool. All right. And again, let's just go back, flip to our code and actually demonstrate this through an example. If we open up the file that we've had, I currently have it looking like this, but I'm just going to comment this line out and do at arithmetic here. And if I do that, the functionality should indeed be the exact same. Just really highlighting the fact that one is indeed a substitute for another. Okay. Awesome. Now, this is very powerful, right? You can now take some other function called subtract and just, and I'm going to be formal here, all you need to do is decorate your subtract function with the arithmetic operator. So if you decorate your subtract function with arithmetic, then it captures the subfunctionality, but it decorates it with some other functionality. That's, by the way, just to give you some linguistic roots of this word, that's why it's called decoration, because what is decorator typically? Think of decorating a house or decorating your kitchen table. You have a typical house, and then you take the fundamentals of the house, you keep that intact, you just add some layer on top, whether it's Christmas decorations or Halloween decorations. Similarly with the dinner table, you have a dinner table, and then you can decorate it for Thanksgiving or for various events. That notion is very analogous to what's going on here with functions. You have some function that has a base functionality, and then you can decorate it by preserving the additional functionality, the original functionality, but adding some custom functionality on top of it. Okay, so that's why the word is called a decorator. It actually does make a lot of sense to call it that. Okay. Now, where does args-quarks come into all this? Well, up till now, our code has been very limiting because add obviously is the function that works on more than just two numbers. It can work on an arbitrary amount of numbers. And we never really want our validate arguments to be restrictive to just taking in two numbers. So why don't we make our inner function validate arguments just take in an arbitrary amount of numbers followed by key value pairs. And in this case, this key value pairs is not actually going to be relevant for our example because our example just consumes numbers, not really pairwise elements. And therefore, all we're going to do in this function is we're going to iterate over the tuple right here. This is, once again, if you recall, this is the tuple. And just make sure every element within this tuple is actually an integer. And if any of them are not integers, just really state that that needs to be an integer. And then finally, we're going to call the operator, whether it's add or subtract, whatever it is, on everything that is passed into that function. Okay. And now this is nice because we can call add with 2 variables. Or if we really wanted to, we could call add with 3 variables. And it would work the exact same way. Okay. Just going back to our example to demonstrate this through code. All we have to do here is change this to be not x and y, but to be star args, comma, star args. And, well, there's no x anymore. What we have to do is we have to say for x in args. And then we can kind of just indent all this to be inside the inside the for loop. And after we've gone over this entire list, what we can do is outside the for loop, we can return operator on star args, star quarks. And keep in mind, this is something that's important to note. If nothing's passed in here in terms of key value pairs, nothing's going to be passed in here. And it'll work like it's only passing in a sequence of numbers. That is something that's very handy. If someone doesn't pass in something here, it just ignores it. Okay. So that's the only thing that changes. And now what's really powerful is we can pass in 3 variables here, x, y, z, and return x plus y plus z. Okay, and then down here we can, well, let's just see it working for one example. We can pass in 1, 2, and 3. And we should indeed, well, let's print this. We should indeed get 6. Okay. Oops. Decorators.py. Ooh, Y is not defined. What went on there? Why is Y not defined? Ah, it's right up here. There's no Y over here. That's part of the previous code that I did not need. Just get rid of those two lines, and now it actually just iterates over all the things that I pass in here. Okay, so to demonstrate this, we do indeed get 6. And now what we can do is we can say, for example, we made a mistake and we passed in the string 1 as opposed to the number 1. Well, now if we run this, and actually, well, that's not giving me exactly what I want. Why is that not? Oh, well, the reason for that, actually, why is that happening? That's an interesting question even for me. That's because over here, it's an interesting case. So this is a problem of debugging or writing code live. You're always going to run into stuff like this, but I actually think this is a very useful tool, because then you guys can kind of see exactly what my train of thought process is when I'm debugging. And over here, what went on? Well, as you can see, this for loop executed, and even if there were things that were not integers, we were still going to be calling operator on args. We were still going to be doing this operation. And so Python would have still done hi plus, or in this case, the string 1 plus 2, and it would have still given us an error. And that's indeed why it gave us an error like this. So what we really needed to do is, if in any of these cases the numbers were not an integer, we indeed here should return none, because then it will never get to this line of code. Okay, so let's demonstrate this now. When we do indeed pass in the string 1 as opposed to the number 1, it does say you need x to be an integer, and it doesn't error out. Okay, so that's really decorators. This at syntax is a short form for doing line 15, and args quargs comes into play because you can generalize this even further by passing in arbitrary arguments to your isolated function. Okay, awesome. So that really concludes our decorators section. Once again, the important takeaways here are, if you can understand add equals arithmetic on add, everything else, I think, really does come together. Decorators are very powerful because it really allows you to isolate a piece of code that you would want to do in many different scenarios. So some examples of this are, well, one we've already seen, error checking. Anytime you have generic error checking you need to do, a very, very good tool to use is decorators, because you can isolate this error checking into some function and then decorate all your original functions with this error checking. Another use case is timing functions. Anytime you want to time a function using like the time library, well, you can just simply isolate the piece of time code and decorate any function that requires timing with your timing function. I actually invite you guys to do that as an exercise. This is just a demo for, well, demonstration purposes. If you do sign up for our course, one of our exercises on this unit actually is the time library and implementing the time decorator. I hope you guys enjoyed the section on decorators. If you are interested, please contact us for more information. And thank you for listening. Goodbye.